Hello. Good day. Right, I think we are in the middle of discussing this proposition that is about the conditional expectation, which is an operator, an operator is a linear function on the space of functions. That's often called an operator. Here we have the L1 functions with respect to the original sigma algebra B. That's the domain of definition for our operator E given A. And the output should be an A measurable function, where A is a subsigma algebra of B. Depending on context, maybe this A is very small, maybe this A is larger, I don't know. The proposition doesn't care. It's true for any subsigma algebra. We want a probability space. So the ambient space is a probability space with a nice sigma algebra, and then we have a subsigma algebra A, and then the claim is already that we have an operator from L1B to L1 mu A called conditional expectation. The property 1 here is the characterizing property. For any function f in L1B, EFA is characterized by those two properties, that EFA is A measurable, and on the sets in A, on Roman A inside script A, the integral of the old function and the new function agree. Maybe I add that to the statement. Property 1 characterizes EF given A for any. I should maybe also emphasize up to null sets, because these are equivalence classes of functions, they're not honestly functions, right? Characterizes EFA up to null sets for any f in L1 mu B. We had some discussions at the end of the last lesson regarding what we should think of this, and maybe I summarize this quickly. So examples to think about. But the beauty and importance of the result is that it's much more general than the examples. We can apply it even if we don't have any clue about what A really is, or what the measure really is. We can still apply it, because we need a measure, and we need a subsigma algebra, but no special situations are required for the proposition to apply. But here I have special situations, and then I can give you formulas for this conditional expectation, or tell you how you can cook up formulas, because I'm lazy. Okay, so one possibility is maybe A is a finite subsigma algebra. So that corresponds to, we have X, and we just chop X into finitely many pieces, and then the sigma algebra consists of all finite unions of these partitions, elements. Or maybe a little bit more generally, X is decomposed countably into a partition, and the sigma algebra is in the same way the sigma algebra you obtain from taking countable unions of atoms from the partition. The sigma algebra then would be uncountable, and then I can't distinguish it from the general case. The general case is more complicated than having a countable partition in the background. I'll give you a second example later. In this case, if you want to know EFA of X, the formula that should be on the right needs to be A measurable, and for this A, which is just the partition, the sigma algebra generated by finite partition, A measurability means that you need to be constant on this piece, because otherwise you would not be A measurable. the preimage of any interval needs to be A-measurable. To be A-measurable needs to be a union of atoms, and that translates to just having the property that on the pieces here, you need to be constant. So I need to give you a formula that doesn't really use X, but only uses the partition element that X belongs to. So what I do is I take 1 over mu of P, integral over P of the original function d mu, where the P is the partition element, where P in A is minimal, with X is in P. That's the partition element that X belongs to. And of course, this we would call conditional expectation. We're sort of assuming X is in the partition element P in this one piece here, maybe in this piece. We're assuming that we're in this piece, and under this assumption that we're in this piece, what is the expected value? Well, the average, of course. So 1 over mu of P, integral f d mu. If one of these partition elements has measure 0, I couldn't care less what the value is. I can also write down something that doesn't make sense. It's okay. I shouldn't maybe, but I couldn't care less. So say 0 if it's not defined. Yeah, and I talked a little bit about it last time, but it was rather quick and I didn't write it down. So maybe X is the unit square. Any product would do for some of the statements, so that's my unit square. B is the Borel sigma algebra, it's so kind of the obvious candidate. But A is the sigma algebra that you get when you take the Borel sigma algebra of the unit interval cross the trivial sigma algebra. So sets in A would look like this. There's a Borel set down here, and then you take everything above that. So things like that. That would be elements of A. Anything down here, cross everything. That's what I mean by this. And I didn't tell you yet the measure, so maybe it's just a Lebesgue measure to begin with. Mu is equal to Lebesgue. Then to be A-measurable means that you are not allowed to depend on the second coordinate, because the sigma algebra doesn't distinguish second coordinates. It distinguishes any first coordinate. So the function can be measurable in the first coordinate, but needs to be constant in the second coordinate. Then it would be A-measurable. So E, F, A at x1, x2 is equal to integral f of x1, y, dy. From 0, 1. You integrate over the second coordinate, just a Lebesgue measure. And why is this satisfying the characterizing property? That's called Fubini's theorem. One holds because of Fubini. But if you do something different, like you maybe still do 0, 1 squared, you still do A equals the Borel sigma algebra on the unit interval cross the trivial sigma algebra on the second coordinate, but mu equals Lebesgue on the diagonal. So it's a one-dimensional Lebesgue measure pushed to the diagonal. Then the conditional expectation will be a different object. It will still be something that is not allowed to depend on the second coordinate, because the sigma algebra is defined in the same way as before. But this time I don't take an integral, I just evaluate the original function on the diagonal So the value on this is the value at the center. And then you just check that one holds because it's measurable. And when you integrate with respect to x1 over the whole space or a part of the space, then really you're just integrating the function along the piece of the diagonal because that's our conditional expectation. But that's the definition of the measure as well. So it's kind of tautologically true that on the left and the right you get the same value. But these are just two examples of two measures, right? You could do some crazy combination of this and that, or maybe you do some measure that has the surface area between two graphs and added to it the Lebesgue measure on another graph, on the third graph. And if you renormalize this to be a probability measure, then the setup is there, and you can now ask yourself what is the conditional expectation, have fun, figure it out. So I'm just drawing a picture and leave it at that. So maybe your Lebesgue measure is, you take the two-dimensional Lebesgue measure underneath the parabola, and then you take the one-dimensional Lebesgue measure on the opposite parabola or whatever, and half of the mass is below the parabola, it's two-dimensional, and half of the mass is on the upper parabola. Then it's a probability measure, and now you can try to figure out what EFA is. And it will be possible to figure out, and you will get some formula that integrates over a piece here and a point and adds the value here, and you will get some convex combination of these two things. And that's where the fun begins. Just try to figure it out what the right formula is. Right? I should, but I didn't always do it. I probably never did it. I should indicate in the notation with respect to which measure we are doing this conditional expectation thing. So it's an E index mu operator. It really needs to know the measure to get the formula going. But the measure is usually the same measure all the time in our discussion. Hence, I usually forget this. I will not fix it there because, yeah. But in these three examples, I use the same space, the same sigma algebra, but different measures, and I always get different formulas. What they have in common is a feature that I want to explain in words, and one can make this into a theorem, but that's sort of a step after one has proven that proposition. So in reasonable situations, meaning the theorem that I'm indicating has some assumptions in addition to what I said up there. In reasonable situations, one can show that EFA is an average of values of f over a part of the space that depends on x. Up there it was the partition element that x contains. Here it was the vertical line that contains our point x1, x2 with respect to a measure, a probability measure, on that part that depends on x and mu. Or, no, it depends on that part, not really on x. I should say that depends on that part and on mu. Meaning, if I know in which vertical line I am, I'm always using the same Lebesgue measure in this example on that vertical line, no matter whether I'm up here or down here. It's the same one-dimensional integration that I do. Also here, it's always the same Dirac measure that I'm using. Over there, it's the same renormalized measure on that piece of the space. For every point in that piece of the space. These probability measures that appear here are called the conditional measures. And again, in these 4 examples, you can write down concrete formulas for these conditional measures. Up there, it's just the measure restricted to the piece, renormalized to be a probability measure. Here, it's the one-dimensional Lebesgue measure, which is a probability measure. Here, it's the Dirac measure on the intersection of the vertical line with the diagonal. But yeah, this is sort of an extra step, requires even a bit more functional analysis and a bit more assumptions. It would be great fun to do that as well, but if we get to it, we will get to it only much later in the course because we have lots of other things to talk about. And for the thing in between, maybe we can first be happy with just the conditional expectation and don't need the conditional measures as of yet. Are there any questions? We had some discussions in the, as I said, and maybe it's now crystal clear what we are trying to do. That's great. But maybe you have still some need to discuss this. Good. So I'll get rid of the examples. I want to keep the statement for now. Maybe I jump a bit back and forth in the statement. Let's start with the end and show that property 1, if a function exists satisfying property 1, called EFA maybe, then this function is uniquely determined by property 1. Let's start with that. It's kind of a warm-up. And I should say the equivalence class of that function is uniquely determined. That's what I should have said. Proof. We start with uniqueness almost surely. Let, how do we call them? H1, H2 be 2 functions that are A measurable and satisfy. I'm thinking real. Of course, everything works real and complex, but let's just think about the real case, because as often in measure theory, if you understand the real case, you understand the general case. And satisfy integral H1 over A d mu is integral F over A d mu is integral H2 A d mu for all A in A, because that's the claim that this is the characterizing property. So I'm assuming I have 2 such functions that satisfy the same equation. We define, as I said, without loss of generality, H, everything is real. We define A to be the set of all X in x, for which h2 of x is bigger than h1 of x. That's in A. Why is this in A? Because h1 and h2 are A measurable. So whatever I define using inequalities and these two functions is an A measurable set. So I can integrate over A and use this property. We obtain integral over A, h2 minus h1 d mu is equal to, or is equal to 0 if mu of A is 0, and is positive if mu of A is positive. Right? Because h1 is bigger than h1. h2 is bigger than h1 on the set A. And a strict inequality integrates to a strict inequality if the set over which I integrate is not a null set. But the second case is not happening because they have the same integral. So this is not happening. So I conclude that A must be a null set. Due to star, we must have mu of A 0, i.e. h2 is less or equal than h1, almost surely. But of course it works the other way as well. So similarly, h1 is less or equal than h2, almost surely. Which gives, and we obtain h1 is equal to h2, almost surely. So of course, on null sets, we might be able to change the function, and we would not notice, because whenever we integrate, null sets are ignored. But apart from changes on null sets, the function h1 and h2 must be the same functions. Let me now go through the list 2, 3, 4 and explain a bit why they are corollaries of 1. Okay. Assuming the existence, for now, let f be greater or equal 0, as in 2. Let A be the set of all x for which the conditional expectation, which we assume to exist, it's uniquely determined by what we had discussed, so I'm allowed to use the symbol EFA, assuming that it exists. I can take all the points where EFA is negative, and again know that this is a measurable set because I defined the set using an A measurable function. Then I can use the characterizing property, integral over my set A of the conditional expectation d mu is equal to the integral over f over the same set, but f is greater or equal 0, so the integral over A of this set of f over this set is greater or equal 0 because f is greater or equal than 0. But EFA is on that set negative, right? That's our definition of EFA. So if we integrate something negative, but the integral is non-negative, then the set A must be a null set. And so mu of A is 0, which is what I wanted to show. I'm ignoring null sets. Right? I should have said almost surely up there, but yeah. and EFA greater equals 0, almost surely. That was the right statement. Good. We keep going. Let's prove 2. Again, I'm assuming everything is real. You need to make small adjustments to the proof in case you're interested in the complex valued functions. I'll leave that to you. What is 2? 2 is the statement that you have a bound, an L1 bound, free. Let F be in L1 B, then what is the one norm of the conditional expectation? That's the integral of the absolute value of the one ball, absolute value over the whole space. That I can split into an integral over 2 pieces. I can integrate over the piece where the conditional expectation is positive, plus I can integrate over the piece where the conditional expectation is negative. Never mind the area where the part of the space where the conditional expectation is 0. But in the second part where the conditional expectation is negative, of course I want to integrate the negative value of the conditional expectation because I'm interested in integrating the absolute value, right? But for each part, the set over which I integrate is A measurable, so I can drop the conditional expectation up here by the characterizing property. So I can rewrite this as the integral of f d mu over the part where the conditional expectation is positive, maybe minus integral over f d mu of the part of the space where the conditional expectation is negative. And now I'm trying to estimate this, right? So I can estimate this by saying I'm taking the absolute value here. Oh, yeah. When I integrate the absolute value of f over that part of the space. Now let me put this again inside, sorry. It doesn't matter, right? Because when I put it inside, I can again say the integral is bounded by the absolute value of f over the other part of the space where the conditional expectation was negative. And those two things add up to, at most, the one norm of f. So I get the statement free. That the one norm of the conditional expectation is bounded by the one norm of f. Right, then there was this fourth property. I'll only sketch it. Sketch for fourth property. What was the statement? That f be in L1, B measurable, G be in L infinity, A measurable, then I already have a formula, namely that I can pull the G out of the conditional expectation. And I get that this is true almost surely. It doesn't destroy the measurability because G is L infinity A, so it's A measurable. So the right-hand side is A measurable. Yeah. So how could we get to that statement? Yeah, I think I was wondering whether we could on the nose get the characterizing property for the right-hand side going, right? Because the measurability is correct. So if we could prove the integral formula for the right-hand side, then it must be the left-hand side by the characterizing property. But I think it's not straightforward. So let me just keep the sketch going and say that there are some cases for which this is easy, and then claim that with those cases you get the general case as well. Again, always assuming existence is already established. If G is the characteristic function of a measurable set A0 in A, then for A in A, we have, in this case, I can check the characterizing property. So what I'll do is I integrate over A, G times my conditional expectation of F. But G itself is also a characteristic function. So what I get is the integral over A intersected A0 of the conditional expectation. But that's an element of A, so I can use the characterizing property. I can rewrite this as A intersection A0 F d mu. But that I can again write using the function G. So I can write it as integral over A G F d mu. Because G is the characteristic function of A0, so this thing is equal to that thing. But if I look at the very left and the very right, I see that this here satisfies the characterizing property for the conditional expectation of the product. Hence, we have E G F given A is equal to G E F given A for this G. What I didn't say, but maybe it isn't so surprising, when I say operator, I mean kind of a linear thing. So the conditional expectation is linear, and that follows quite trivially from the characterizing property, because the left-hand side is linear, the right-hand side is linear somehow, and it's really no big surprise that that makes the conditional operator, assuming existence, a linear operator. So if I now take a linear combination of G's, of characteristic functions, simple bounded functions, then this will also be true, because left and right-hand side will change linearly if G is a linear combination of characteristic functions. Hence we have this. Using linear combinations, this extends to simple bounded functions. Having it extended to simple bounded functions, we can now take a limit. We can write every bounded function as a uniform limit of simple bounded functions. And then you're going to use property 3, which tells you that the operator is a continuous operator. It's decreasing norms. So if something converges in L1 and you apply the operator, you get something else that converges in L1. Yeah, so it's a sketch using that any G in L infinity is a uniform limit And property 3, which we already know, the general case follows. And property 3, was it 3? Yes, 3 is still up there. The general case follows. Okay. It's time to attack the existence, right? So we now want to show the existence. I gave it away already last time because we do this in 2 steps. First, we say, suppose for the moment F is in L2. L2 is contained in L1. In a probability space, that's how it works. We first treat the case F in L2 B. Let P be the orthogonal projector from L2B to L2 mu A. Okay, we need to review a little bit of measure theory functional analysis here, but I'll just do this verbally. I don't write it down. So what's the functional analysis that we need to know, the Lebesgue integration that we need to use? We want to know that L2 mu B and same thing for L2 mu A are complete spaces. Every Cauchy sequence in L2 has a converging subsequence, is converging. That we'll know from measure theory. That applies to any sigma algebra in the world, right? So it applies to this guy and to that guy. So they're both complete spaces. There's something else that's nice about complete spaces. If a complete space is a subspace of another one, then it's automatically closed. So this is complete, and it's a subspace of this one, so it's actually a closed subspace of this one. And then you just discussed, well, you already know, maybe since a long time, or maybe not since such a long time, that you have an orthogonal projection in Hilbert spaces to subspaces. And it goes, maybe just a quick reminder, it goes through Riesz representation. So if you take an element here, then it gives you a linear functional here. But the linear functional you can restrict to a subspace. If it's a closed subspace, you can apply Riesz representation on the closed subspace and represent that inner product by something here, by an inner product with something from here. And that's called orthogonal projection. Gives you the best approximation. There are many other things you can say about this, but yeah. It's the orthogonal projection from that closed, that complete space to this closed subspace. That exists just because of nice properties of L2 spaces and because of measure theory giving you completeness. We claim that PF belongs to L1 mu A and satisfies the characterizing property. So we get existence if F is an L2. Okay, so let's check that. I want to know that it's in L1. which is actually the same thing that we did already. It's the argument up there. So let me just check the characterizing property and then point up to that thing here. So let me check the characterizing property. Let A be an A. Then the characteristic function of A is in L2 mu A. So it's in the subspace to which we did an orthogonal projection. And hence, when I look at my original function, inner product with the characteristic function of A, I must be getting the same thing as when I do the inner product with the orthogonal projection, because this vector belongs to my subspace to which I did a orthogonal projection. That's this formula. But now I rewrite what this means in terms of actual integrals. My inner product is precisely defined by the inner product, by the integral. So this is actually the same thing as, lo and behold, the characterizing property that we were after. Because inner product with a characteristic function is just integrating over that subset. As in 3 above, I'm lucky that it's still there, so we can point at it. This also implies that the one norm of P of F is less or equal than the one norm of the original function. Because this property holds for all A in A, and if I do this decomposition into wherever E of F A is positive and wherever E of F is negative, if I do this decomposition and go through this argument above, I get this inequality, which tells me that P of F is in L1. Right? It wasn't obvious because P was an orthogonal projection to the L2 space. But if you start with something if you start with something in L2, no, it was obvious, never mind. We ended up with something in the L2 space. The L2 space is contained in L1. So it was obvious that we had an L1 function. But anyway, we also have this inequality. Never mind, we didn't need that. Sorry for the confusion. We are still going to need that. Because now I want to use density of L2 inside of L1 and obtain this way a method of obtaining the conditional expectation for an L1 function. But I guess I do this after the break. Good. Of course, I talked about the orthogonal projection and so on, but I didn't put it here somehow. I forgot. Be the orthogonal projection. Yes. And now we wanted to read the general case. Suppose now f is just in L1, so the square might not be integrable anymore. B. Then there exists a sequence Fn in L2. It's unclear whether my 1s and 2s are sufficiently distinguishable this time, but yeah, hopefully sufficient. There exists a sequence Fn in L2 of B with Fn converges to F in L1. because simple functions are dense, right? Simple functions are in L2, so I can write my f as the limit of a sequence in L2. For each one of those fn's, I already have the conditional expectation by using the orthogonal projection. We use P for Fn and obtain. When we look at P of Fm minus P of Fn, one known, that's P of Fm minus Fn, one known. That's less or equal than Fm minus Fn, one known. Because this is what we checked here. But the Fn is converging in L1, right? Converging to F. So the Fn's are a Cauchy sequence. And the P of Fn's have smaller distances than the Fn's have. So these guys are also a Cauchy sequence. This implies that P of Fn in L1 of A is a Cauchy sequence. And so has a limit in L1 of A. Let's call it H. H in L1 of A. I need a tiny bit more space because, of course, now the game is that this H is our conditional expectation. The H satisfies the characterizing property. And it's a limit in L1, right, with one norm. For A in A, we now have, I'm interested in the inner product of A over H d mu. But H is the limit of the P of Fn's, right? So limit n goes to infinity over integral over A P of Fn d mu. That's true because of, say, dominated convergence or something. It's kind of an automatic consequence of H being the limit in L1. Because A is L infinity and F, yeah. It's easy. But for the P's, we know we checked up there the characterizing property. So that's the limit as n goes to infinity of integral over A Fn d mu. And then the same thing happens here. The Fn converges to F. So this is the integral over A of F d mu. Therefore, H equal E Fa exists. End of proof. Finally. So we can keep move the measure theory again into the back of our mind and keep talking about ergodic theory. Any questions? Good. So, what's the ergodic theorem? We already had an ergodic theorem last week. That was the mean ergodic theorem, where we had convergence in L2, just L2. And now we want to upgrade that statement in two ways. We want to make a statement for L1 functions, and we want to make that statement a pointwise statement, an almost sure pointwise statement. And that's the Birkhoff pointwise ergodic theorem. Or also called individual, because we look at an individual orbit instead of sort of the average behavior. Big-off pointwise ergodic theorem. It's still a very general statement. We need a probability space. X, B, mu, be a probability space. And we need a measure-preserving transformation, T. And yeah, at some point we need to discuss how to find invariant measures. We'll get to that. But now we assume that we have such a thing. And we have seen examples where this existed already. For f in L1, mu b, we have, when we look at the ergodic averages of the function f, a(n) of f is equal to 1 over, let me write, of x equals 1 over n, sum k from 0 to n minus 1, f of t to the kx. So we are looking at a piece of the orbit and averaging over a piece of the orbit. And when n gets bigger, we average over a bigger and bigger piece of the orbit. This converges to the conditional expectation of f with respect to a sigma algebra that I want to call ET, E sub t. And this convergence holds for n goes to infinity. In L1, and almost surely for x and x pointwise. So the set of x for which this convergence is not true is a null set. Where, I need to tell you what this E of t is, where E sub t is the set of all B in the Borel sigma algebra, in the sigma algebra B, such that T inverse of B equals B. There are a couple of proofs, of course, around of this theorem. It's a very classical thing. Some of the proofs go via a maximal ergodic theorem, which is a slightly stronger statement. I'm not sure whether we need that. If we need it later, we'll think about it later. I'll give a shorter proof that uses still some of the ideas of this maximal inequality kind of approach, but is much shorter. I think for a first introduction into the subject, it's a good compromise. Yeah, good. So this is what we want to show, right? We want to, yeah. Definition, no, proof. We start with a definition because we are in the middle of the proof, or in most of the proof, we actually don't look at the average, but at the ergodic sum, where we don't divide by n. For h, a function on x, we define S0 of f h. It's stupid, we sum over 0 terms, so it's 0. Sn of h equals h of x, Sn of is h of x plus h of tx plus h of t to the n minus 1x. So we sum precisely over n terms. So S1 of h would be just this term for n in n. Yeah, we are given some function and want to prove something for it. So fix some f in L1 of x and fix some epsilon greater than 0. and define sort of a helper function, g of x, which is f of x minus its conditional expectation for the sigma algebra, and minus an epsilon. This is in L1. We wish to show that when I look at the lim sup, as n goes to infinity, of 1 over n, an of f, that this is always less or equal than 0. Almost surely. Because if you chase it, it's sort of just telling us that up to an epsilon, the average of f is eventually below the conditional expectation plus epsilon. If we know this, we get half of the statement that we want for the fixed epsilon, but if we know it for a fixed epsilon, we know it. Because there are only countably many epsilons, so there might be countably many null sets that we need to take the union of, but we would get half of the statement, and if we have this half of the statement and replace f by minus f, we get the other half of the statement. Okay. I said we are going to use the sums a bit more than the average. Sorry. The average is the average. You don't need to divide the average by n. Sorry. That's nonsense here. Good. I defined a set and I called it A, which is unfortunate because it clashes with that a bit, but never mind. We define, how else do we want to call it? I want to call it A. A is the set of all x for which the sup over k greater equal 1 of sk of x is positive. No, it's infinity. Okay. The claim is that this is a null set. And then I'll tell you what this all tells us. Claim mu of A is equal to 0. Assuming the claim, we would obtain this statement here. Because if I have a point for which the average has a lim sup, a positive lim sup, then this point needs to be in the set A. Because if the lim sup of the average is positive, then the sums along a subsequence need to go to infinity. So what's the issue? So is it sk of x? Right. So what's the sk? It's the g that I'm using, and I think I want to, sk of g of x. Thank you. G of x. Also here, that's the g, sorry. Assuming the game, we obtain star. If lim sup, let's try to write down a few things without confusions. Lim sup of an of g is positive, then along a subsequence, S n g at x is positive, then along a subsequence, S n g of x will go to infinity, and so x will belong to A, as mu of A is 0, we obtain star. Using linearity, of A n of G, we also obtain from this for a little while I keep the theorem alive. What's the an of G? That's the an of F minus the an of the expectation of F with respect to this ET thing, and then the average of epsilon, well, the average of epsilon is epsilon. And if I already know, now what's the average of this EF given ET? This function here is ET measurable. And what is ET? ET is the sigma algebra of invariant sets. So when I take a pre-image of an interval under the function, under this conditional expectation function, when I take a pre-image of a characteristic function, I always get an invariant set, right? Because ET consists of invariant sets. That actually means that this expectation is an invariant function. Because for every interval, the pre-image of the interval will be an invariant function, will be an invariant set. So whether my point is in the set or the image point is in the set, it's the same statement because the set is invariant. And if this is true for all pre-images of characteristic functions, then the value of my function and the value of my future point would need to be the same. Okay, people are confused with this. So let me explain this a bit more. This is subclaim for this discussion. If I have a function, let's give it another name, h. If h is ET measurable, then h composed with t is equal to h, and the average of h is h, because this follows from that here, right? So then, if I use this subgame, I get here the average of f minus the conditional expectation of f given et minus epsilon. So I get a much simpler expression from averaging G than I originally had. Okay, how do I prove that? Given an interval I in R, I'm again just working with real valued functions because currently there's no point in using complexes. Given an interval I in R, A equals H inverse of the interval is T invariant because it's an element of ET. That's ET is defined like this. Hence, X in X satisfies, any X in X satisfies that H of X is in this interval if and only if h of t of x is in this interval, because that describes the preimage, and that describes the preimage of the preimage, right? So that this is equivalent to x being h inverse of this interval. But we said that this set is equal to its preimage because the set is invariant. This set is equal to its preimage. But that's this property, that x is in here if and only if h of t of x is in E. And it suffices, yeah. If you know that statement for all intervals, then you know your h of x is equal to h of t of x, right? With intervals, you can test the value, you can pinpoint the value precisely, and you only need countable many intervals, which isn't particularly relevant right now. So this function is invariant. This function here is invariant, so if I average the invariant function, I just get the function back. I get this function. So what do I get? I want to our claim is that this funky set here has zero measure, right? I'm assuming the claim, if the claim holds, then the lim sup of this an of g of x greater equals 0 can only be greater equal to 0 for a point in A, so we would obtain that an of g is less or equal than 0. But an of g, I calculated up there a bit more precisely. It's an of f minus stuff. And the minus stuff doesn't depend on g, so star is actually equivalent to a different statement where I see the average of f appearing. So this is equivalent by the calculation up there to star prime lim sup over an of f is less or equal that the expectation plus epsilon, almost surely. If we know this for all epsilon greater than 0, then lim sup an of f is less or equal than the conditional expectation. If we know this for f and minus f, then by using minus f here and here, and then multiplying the whole thing by -1, lim sup becomes lim inf, and the inequality goes in the other direction. I actually get that the limit of an, sorry, there's an almost surely here. Almost surely, over there I had an almost surely, then lim an of f at x is equal to ef given et, almost surely. Which is what we wanted to prove, right? That's the theorem, which I still have. The pointwise part of the theorem. So this gives us the pointwise part of the theorem. This is the claim that we need to show. Now I erase everything. And there's a bit of trickery how to get this, but it's kind of, yeah, it has been condensed and condensed over generations, and it's a cute proof. Yeah, I think the pointwise statement we should be able to get, so let's aim at that in the remaining time. Good. So there are a few tricks to be had. Note that I need to relate somehow what happens at x and what happens at t of x a bit. So I take sk g of t of x, and I want to compare this to sk plus 1 g of x. But of course, this is the sum starting at g of x, and this is the sum starting at g of t of x. So for the sum starting at g of x, I need to subtract g of x, because this is not appearing over here. But apart from that, that's an equation for k greater equal 0, greater equal 1. Right here I'm summing over at least one term, and I here have a sum over one extra term, but I remove the first one, and then it's the same thing. Okay? I still have the definition of A up there, and if I look at that and look at the definition of A, if x is in A, then along a subsequence this will go to infinity. This is a value, right? This is a real number, not changing along the subsequence. So if x is in A, and this goes to infinity along a subsequence, this will go to infinity along a slightly shifted subsequence. And the other way around, if t of x is in A, this will go to infinity. This is the same all the time, so this will need to go to infinity along a shifted subsequence. So x is in A if and only if t of x is in A. So A is a set of E of t. This implies A is in ET. Because x is in A if and only if, or t of x is in A if and only if x is in A. That's what I explained. That's the proof of A being invariant. And of course, it's a measurable set, right? It's up here, we define it very precisely using measurable functions, so it's a measurable set. We now define the maximum of the SKs. So for n greater equal 1, we define mn, and I forget the g and the x because they're fixed. Mn is the maximum of the SKs, where the maximum goes including with 0 up to n minus 1 probably. N doesn't matter. N, which I just write it out again. It's the maximum of 0, of g of x plus g of t of x, comma, and so on, up to g of x plus g of t to the n minus 1x. It's the maximum of all of these terms. Because Sn is the sum of n things. That's how we define the Sn. So here we have, at the last point, we have a sum of n terms. And the Mn is the maximum of all of these for our helper function g. And somehow, similar to this, we want some kind of formula for Mn linking what happens at x and what happens at t of x. And it's difficult thing is to know what to write down, so that's why I look at the notes, but it's not supposed to be a difficult thing. Then m n plus 1 at x is equal to, yeah, let's say this, let's not keep the x a secret, otherwise it gets confusing. So the x is part of the definition. Mn plus 1 of x is the maximum of 0 and g of x plus mn of t of x. Which, if you stare at the definition long enough, it should be obvious. Because if we take mn of t of x, we get this maximum where we have g of t of x plus g of t squared of x plus up to t to the n of x in the last sum. But the g of x is missing all the time. So we add to it g of x. And then we get the maximum, so this here is the expression maximum g of x plus g of t of x up to where we have here n instead of n minus 1. We're missing the maximum of 0 because maybe all of these things are negative, so we add a maximum 0 in front and then it's tautologically the same. If you agree, that's good. And now we do some trickery with that. We subtract this guy. So we take mn plus 1 of x minus mn of x is the maximum of minus mn of, sorry, t of x, mn t of x, comma g of x. And we're interested in points in A, where the A is the definition, where the sk goes to infinity. So now we try to use that our x that we're interested in is in A. For x in A, we have sk g of x going to infinity along a subsequence. And so the maximum, the mn g of x, definitely going to infinity as n goes to infinity, right? Because the mn is defined here. If this goes to infinity along a subsequence, then the mn will just straight away go to infinity because it's the maximum. Which tells us what this difference is going to do, because it's the maximum of something that goes to minus infinity and g of x. Right? Hence, for x in A, we have mn plus 1 of x minus mn t of x going to g of x, because it's equal to this maximum, and this function is at some point negative. So at that point, the maximum will be not just negative, will be g of x might also be negative. This function will at some point be really going off to minus infinity and be smaller than g of x. So at that point, this difference will be equal to g of x. I don't know when it happens, so that's why there's a convergence. Okay, if I have a convergence on a set of function, maybe I can integrate this and use this to get something. So I would like to know whether whether this is dominated, this convergence. And mn is non-negative, right? It's a maximum of 0 and something. So mn is non-negative. So there should be a nice inequality coming out of this statement. So a maximum of two functions is greater or equal g of x, and it's also less or equal than the maximum of 0 and g of x. Because as I said, this here is less or equal than 0, and if I replace something with an upper bound inside a maximum, I get an inequality. That's obvious. But g is integrable, and this maximum is integrable. So I have sandwiched the sequence of functions between two integrable functions. So I can apply dominated convergence to this thing on A, right? On A, I have this convergence. The sequence is sandwiched between two integrable things. I can use dominated convergence and get a formula involving integrals. Yeah, let me give this two labels. Combining this guy and the other guy with dominated convergence, we obtain limit n goes to infinity integral. I'm only allowed to integrate over A because the convergence happens on A. mn plus 1 of x minus mn t of x d mu is equal to integral over A g of x d mu. And now I keep going by integrating the right-hand side, or calculating a bit more the right-hand side, calculating a bit more the left-hand side, and something will come out of it. Note, integral over A g of x dx d mu is equal to integral f minus the conditional expectation with respect to the invariant sigma algebra minus epsilon d mu. But A is precisely a set from in here, from this ET. A is an invariant sigma set. So the first two expressions cancel each other. So this is an ET. So what comes out of it is minus epsilon mu of A. Okay? Now I want to calculate the integral in the middle, on the left-hand side a bit more. Also, integral mn plus 1 of x. Now let me just look at the mn of t of x initially. Integral over A d mu, so this expression here. That's the same thing as the integral characteristic function of A, or T inverse A, it's the same thing. Mn Tx d mu is equal to integral characteristic function of A, Mn composed with T d mu. Right, and we had last week we had a lemma saying that if we compose with T and mu is an invariant thing, this is irrelevant. So I can skip that composing stuff. So I just write integral over A, mn d mu, and I didn't change the integral because mu is T invariant, or T is mu preserving. That's the substitution lemma. Aha, so the T here in this expression isn't particularly important. I can kill it off. And so the integral over mn plus 1 of x minus mn of t of x d mu is equal to the integral of mn plus 1 of x minus mn of x, always over a d mu. Now there's something happening, which again, every step is kind of obvious, and this is another step that's kind of obvious, but how to fit them together is less obvious. What's that? That's the maximum of the ergodic sums. Up to n plus 1. That's the maximum of the ergodic sums up to n. So this is bigger than that. So we're integrating something non-negative here, by definition. So we get something non-negative. But the integral, the limit of the integrals looks kind of negative. Well, can't be, so it's not, it's really just kind of. The measure of the set needs to be 0. That's the only way out. Yeah, and that's what we wanted to prove, and that gives you the pointwise statement, and I really optimized the time so that I'm done with it, the pointwise thing, when the gong appears. And I might still have time to finish the statement on the board. Combining these two, we obtain mu of a equals 0. And so, as explained, the pointwise convergence. Almost. Almost. Thank you. Unless you have questions.